here we go. All right. Theoretically, we're live. All right. And so where are you right now?
I'm now in Luxembourg.
Okay. Isn't like the whole space agency just in Luxembourg?
Yeah, there's a national space agency, the
Yeah.
Luxembourg Space Agency.
Yeah. All right. Well, I guess we started. So who are you? What do you do?
Yeah, my name is Andreas Hein. I'm currently based in Luxembourg. I'm a professor at the University of Luxembourg, SNT, which is a multidisciplinary institute within the University of Luxembourg. And I'm also the executive director of the Initiative for Interstellar Studies, which is a UK-based not-for-profit company working towards interstellar travel.
Very cool. And I'm sure this is going to cover a lot of people's topics they're really interested in. So I guess, how hard is it to go to another star? I mean, we're very familiar with how long it takes to send spacecraft to Mars, how long, New Horizons took 10 years to get out to Pluto. The Voyagers are still flying out there. Put that in context to attempting to cross the distance between here and, say, the nearest star system.
Yeah, getting to the nearest star, like the Alpha Centauri system, is incredibly difficult. Just to put it into context, if we take the distance between the Earth and the Sun and say, okay, this distance is 1 meter. Yeah, so let's compress 150 million kilometers into 1 meter. Okay? On that scale, that the farthest humans ever got in space, like to the moon, that would be like less than 1 millimeter
Yeah.
in size. Yeah, so that's like the farthest distance humans have ever gone. Now, on that scale, going to Mars would be, depending on Mars is, it's maybe like 1 meters, 2 meters, 3 meters further away from Earth. And if we want to go to Jupiter, Saturn, it's like, I don't know, 7 meters, 9 meters, something like that. Yeah. So you can easily imagine that this, on that scale, this is like easily imaginable. Now, when we talk about the farthest human-made object, which is traveling in space, the Voyager probes, I think to the last estimate, I think they are like about 150 astronomical units away, something like that. Then that would be 150 meters. Still, you can imagine how much 150 meters are. Easy to imagine. Now, the distance to the Alpha Centauri system on that scale would be about 260 kilometers. So just think about from where you are, where 260 kilometers are.
Yeah.
So it's incredibly far away. I mean, this is like on a European scale, that's like the distance between like Munich and Stuttgart or Paris and Strasbourg. So it's a complete different scale on which we are. And that's the challenge of interstellar travel, crossing these distances in acceptable amounts of time.
Right. And I guess that's the thing, the acceptable. Like, the Voyagers are on their way and they will cross that distance. It's just going to take them 50,000 years and they'll be long dead and not even going in the right direction anyway. But if you were patient enough, you could send a mission to another star system. You just have to be willing to wait a long time and build a very robust piece of equipment. So what is the kind of time frame that the folks at the Interstellar Institute are targeting?
That's a great question. I mean, in the space domain, we sometimes have this joke like getting humans to Mars is always like 20 years into the future. Yeah, I mean, there are similar jokes for fusion energy.
Well, I'm more talking about the amount of time you'd like to see the flight take, as opposed to when you think we'll actually begin the set out on the journey.
Yeah, I mean, There are different answers to that question. We are, for instance, collaborating with Breakthrough Initiatives, Breakthrough Starshot, and if we take Breakthrough Starshot, which is probably like the most sophisticated project working on interstellar travel today, they are thinking about getting to the Alpha Centauri system in maybe 20 years, 30 years, depending on the latest estimates. So we are talking about a few decades. That's, of course, for a very small spacecraft, gram-scale spacecraft. But if it's just for getting something to another star system, I would say a few decades should be feasible in the midterm future.
Right. And so what is the technology that you feel is most feasible at this point to be able to carry on one of these missions?
Yeah, that's a great question, because there are still a lot of debates within the interstellar community about which propulsion technology to look into. Fortunately, today we're in a situation where various organizations, various groups are working on different types of propulsion systems, and that's probably a good strategy, because all of these technologies are at a relatively low level of maturity, and then it's always good to have several alternative technology paths, because if one path doesn't work out, you can still move to other path and see if those technologies work. I would say just based on the maturity of the technologies which exist today, I would say that laser propulsion system, so what Breakthrough Starshot is currently working on, is probably the most feasible way of getting something to the stars. But it very much depends on the requirements. If you want to get a heavier payload to the stars, then it's quite difficult to do with any sail-based technology, which means that you would have to move to maybe something like fusion propulsion.
So then we'll talk about the sail-based first. And we know in broad strokes what this involves. You take a big laser and you shoot a tiny spacecraft solar sail and you accelerate it to relativistic speeds. What are the big, I guess, unknowns? What are the current technological hurdles in going from a cool idea to perhaps an actual working prototype?
That's a great question. Breakthrough Starshot has done a great job to list these areas where progress needs to be made in order to make laser-based interstellar propulsion a reality. Just to give you a few examples, one is, for instance, communications. Yeah, how do you get data back? Because even if you go to another star, ultimately what you want to have is getting data back in order to explore that star system. So communication is a huge issue. The second point is, how do you protect a very lightweight spacecraft against impact from interstellar matter, interstellar material, dust, particles? Another question is, how do you generate enough power on board? Because interstellar space is very dark. You have to essentially take your power source either with you, or you have to somehow maybe beam power to the spacecraft, or you might need to use some environmental effect in order to generate power. So it's very challenging to get that power source on a very small spacecraft. You could think about nuclear batteries, for instance, but this is an unsolved issue right now. And all these challenges, which are really associated with the laser and the sail itself, how do you coordinate millions or potentially billions of laser diodes in order to generate one coherent beam? So this is something which hasn't been done yet, not at those power levels and those durations. How do you make sure that the sail doesn't melt or evaporate because of the extremely high power densities? We are talking about maybe hundreds of gigawatts per square meters. Yeah, so maybe 100 gigawatts per square meter. That's a much higher power density, as to my knowledge, like in a fusion or nuclear reactor.
Mm-hmm.
Yeah, we're really talking about power densities which haven't been encountered in any propulsion technology yet. So we need to solve that with materials which are highly reflective, which essentially do not exhibit any defects, but still at the corners of the sail, for instance, you might naturally get some a place where heat could creep into the sail and thereby gradually evaporate the sail. So I would say these are like two of the major issues with the laser propulsion system itself. But there are other issues, such as how do you keep the sail stable in the laser beam, because it's accelerating at an extremely high rate. We are talking about 10,000 Gs. So 1 G is the acceleration we experience on Earth when we stand on Earth. So here we are experiencing like tens of thousands of Gs. 10 G is already can be lethal for humans. So here we are talking about the acceleration which is experienced like by artillery shells. So the spacecraft needs to withstand these levels of acceleration and stay stable in the beam.
Yeah. It's a long list of engineering challenges that need to be figured out. Then, you talked about some other ideas, fusion, antimatter. So what do you think? I don't know if you saw, there was a paper, someone had done a recent debunking of the Bussard ramjet, that it's essentially infeasible. There's just not enough hydrogen in the interstellar medium to be able to make a Bussard ramjet. So if you did want to do, say, a fusion engine, what do you think is sort of the most feasible way to go that route?
Yeah, again, a great question, because fusion propulsion, when we talk about fusion propulsion, there are different types of fusion propulsion systems. I've been a member of the Project Icarus team, which revisited the Project Daedalus design from the 1970s, which was essentially like the first sophisticated design study of an interstellar mission. And the idea was to, looking back 30, 40 years, how much has technology advanced in terms of fusion propulsion or interstellar spacecraft technology, and to revisit and reevaluate whether that mission could be done with the technologies we can expect to exist in the near future. Now, I would say that many of the challenges coming with this type of fusion propulsion, which is essentially pulsed fusion propulsion, so you're having pellets of fusion material. In the Daedalus probes, this was like deuterium, tritium. And in the new Icarus design, we are more focusing on helium-3 and tritium. And these pellets are essentially ejected into the nozzle. And then you have lasers, or with Daedalus, these were like electron guns, and they would essentially compress that pellet to levels where the fusion reaction is ignited, then energy is released, and the exhaust products are then channeled via a magnetic nozzle away from the spacecraft, and that generates the thrust.
And that sentence that you just used, I think, had about 5 things that are probably very difficult engineering challenges to overcome.
Yeah.
The having helium pellets hit with high-powered lasers, magnetic bubbles channeling the thrust, et cetera, et cetera. But does the math hold? Like, if you could do all those things, if you could pelletize helium-3, if you could ignite it with lasers, could you hold enough fuel on board a spacecraft to be able to perform your acceleration and, I guess, deceleration at your target star?
That's a great question, because the feasibility of the mission really depends on the efficiency of some of these processes. Like, if you ignite the pellet, what percentage of the pellet is ignited and transforms into energy via the fusion reaction. What's the efficiency of the nozzle to channel those exhaust products away from the spacecraft? If you take all these efficiencies, and if you don't get very high efficiencies for each of these values, then it might turn out that the spacecraft doesn't get up to the necessary speeds. So it's really, I think in terms of math, we've run through the equations and everything could work, but really the devil is really in the details, and really in these efficiencies, whether you can reach these efficiencies. Because if you can't, then it will take really hundreds or thousands of years.
Right. So it's like if in the sort of perfect world, if you can get the efficiencies as high as possible, each part of it, then you have a chance of it working and giving you a reasonable speed. But so far, we haven't been able to do any of these things, even here on Earth, not to mention out in space, not to mention moving at relativistic speeds with a machine that runs for decades, completely automated, et cetera, et cetera, et cetera. So then let's talk about the antimatter. How does that work?
Yeah. Antimatter is an interesting case because I think the main argument why antimatter propulsion is dismissed today is because of its extremely high cost. And usually people then cite the cost of operating CERN and how much antimatter is generated inside CERN, the particle accelerator. But I guess this is probably a flawed argumentation, because if in the future we are going to generate antimatter in substantial quantities, we're certainly not going to use CERN. It's going to be a device which is much more efficient in generating antimatter. And there have been different concepts out there. And I think on a regular basis, I'm reading articles in the press where somebody found a more efficient way to generate antimatter. So I think the cost argument probably doesn't really hold.
Mm-hmm.
And but one of the technical challenges of antimatter is how to store it, because obviously antimatter shouldn't be in touch with normal matter, because then you get a lot of energy out of it. So you would like to avoid that. And typically people propose magnetic bottles. So you're essentially sealing antimatter into magnetic bottles. But I'm not aware of more recent research that has really looked into efficient and maybe lightweight magnetic bottles and how we can store antimatter there. So I would say antimatter is maybe an overlooked or underestimated technology right now, and it might be interesting to have a closer look.
Well, I guess I just wonder, like, I mean, antimatter is just kind of like a battery, in that you're putting an enormous amount of energy in, you're generating a material which will then, when it actually interacts with regular matter, will deliver you energy at a pure 100% ratio. Obviously those are the, how can you generate your antimatter efficiently? But you can do it here on Earth in a giant factory. As you say, you can, right now, I think it's like $69 trillion a gram or something for antimatter. So yeah, that's expensive. But you can imagine orders of magnitude being knocked off that price. And because it's down here on Earth, you can actually just, build it. The containment sounds like a solvable challenge. So I guess the question is then, if you did have a block of, or I guess a cloud of antimatter that was in a containment bubble, what kinds of, and you could then, the rest of it sounds simpler, that you pull out these atoms one at a time, mash them with regular matter and use the energy as for your exhaust. How does that work? Like, I guess, how efficient is that? How well would that system work as a means of an interstellar mission?
Yeah, again, a great question, because nobody knows right now. So, and probably the feasibility of antimatter propulsion also depends on these efficiencies. So broadly speaking, there are like two categories of antimatter propulsion systems. one is based on pure antimatter reactions. So you're bringing matter and antimatter together, and you're generating energy and some elementary particles such as pions. Yeah, and pions are negatively charged, which means that you can essentially thrust them out into one direction with a magnetic nozzle. That would be like really the pure antimatter rocket. The problem with this type of rocket is that the specific impulse, so essentially the efficiency of the propulsion system is extremely high. However, the thrust is extremely low. And that's a problem because you would need a very long time to accelerate the spacecraft. Now, typically, antimatter propulsions of the second category are propulsion systems where you are exploiting the energy which is released from the antimatter reaction, and then you're injecting some form of propellant into that released energy. And then the propellant would be heated up and then exhausted out of a nozzle. This is, for instance, like the gas core antimatter rocket. It's essentially based on that kind of principle. So you are releasing energy with the antimatter reaction. You're injecting propellant, and then you're essentially the heated up propellant is then exhausting.
Sort of the same idea as a fission nuclear rocket, that you're using the fission reaction to heat up usually like a hydrogen gas as your propellant, and you get a much higher exhaust velocity than you would with a pure chemical rocket. So you're taking advantage of the additional energy to give you a faster exhaust velocity, but it's nowhere near as efficient as the original. What do you call it? Prions? I hadn't heard that term before.
Pions.
Pions, yeah. Pions are the things you get in your brain. Yeah, pions. Right. And so that feels kind of analogous to an ion engine, that you're taking individual atoms, accelerating them in a magnetic field and throwing them out the back of the spacecraft, but supercharged with antimatter style. So is that it? Is that our list? I mean, obviously, people are going to want to know about warp drives and M drives and all of that. What about photonic propulsion?
Oh, you mean solar sails?
No, like you shooting a laser and using
okay.
using that as getting the reaction from as photons are leaving your spacecraft at the speed of light, you get a kick in the opposite direction.
Okay. Yeah, that's an interesting concept because Eugen Sanger, one of the pioneers of astronautics, proposed the photon rocket. I think it was in the 1950s, and he proposed a pure photon rocket, which essentially works like having a laser at the back of the spacecraft and then having the laser itself as a propulsion system. So this would work. However, again, the thrust would be very, very low compared to the energy or power you would need to put into. Just to give you an idea, in order to get a few newtons of thrust, so 1 Newton is about the weight of a bar of chocolate. So if you have like 1 gigawatt, which is the power output of like a small nuclear power plant, and you would channel that into a laser, the laser beam would generate a thrust of about 4 newtons, so 4 chocolate bars.
Right.
And it's incredibly inefficient. And that's also the reason why for Sanger's rocket to work, you would need extremely high power densities in order to get some reasonable acceleration out of it.
Right. So I did a video, and there's a fairly famous paper out there called the weight calculation, and I don't know if you've looked into this, and the gist is like if you take the energy requirements to send a spacecraft to another star system, it's actually enormous compared to anything else that we do. And if you take the rising exponential curve of humanity's energy output, those two lines cross about 700 years from now. So are we just too early? Like centuries too early to to try to accomplish this goal?
Okay, so this is a different type of weight calculation I'm familiar with.
Sure.
I mean, the typical weight calculation is like we should wait to launch a spacecraft even if we could do it now, because the propulsion technology advances
Right.
so fast that if you launch it in 50 years, that probe would essentially take over and
Right.
be quicker.
Yeah, so sorry. So just like the calculation that the researchers had done is what is the optimal time that there's a certain sweet spot where you can't launch a faster spacecraft. And so you won't overtake the spacecraft. And that number is about 700 years in the future. That any attempt to launch a spacecraft before that time, we will figure out a way to launch a faster spacecraft and overtake it until about that 700-year mark.
Yeah, I think the weight calculation, the argumentations I've seen, in my opinion, they are deeply flawed for the reason that, first of all, there are weight calculations which are based on this exponential increase in like energy generation, advances in propulsion systems, etc. But the basic assumption behind these calculations is that we are essentially living in a normal time, and things will continue like this in the next couple of centuries. I think we are living in extraordinary times on the timescale of humanity. If we look at the last 200 years since the Industrial Revolution, if you look at, for instance, GDP growth, energy growth, all of these parameters which are typically associated with wealth, healthcare, etc., you can see exponential effects in almost any area of our lives. And this is absolutely extraordinary. If you look at human history for thousands, 10,000s of years, we never had this type of drastic change, which means that assuming that things will continue like this for the next 100 of years, based on the last 200 years, I think this is like flawed reasoning, in my opinion, because if we look at today's developments, GDP on a global scale tends to decrease. The more developed nations are, GDP seems to stagnate. Energy consumption seems to increase, but there's also a trend of stagnation in the wealthy countries in the world. We also have technology-wise, this is also, I think, people have the perception that today we have a exponential increase in technological progress. We're very far away from that. If you look at what happened in the 19th century, there's actually a very, very good book exactly about this period of time written by an economist. And you can see that the progress which happened between AD 50 and 9050 is orders of magnitude away from what we're experiencing today. I mean, just if you experience what somebody from 8050, if you put that person, just take 9010. I mean, you have airplanes, you have steamships, you have telephones. All of these technologies have profoundly changed the lives, and I can see the same progress in the last 50 years, 60 years at the same level impacting our lives. So the basic idea that progress will continue like this centuries into the future, I think this is, I don't think this is very robust to base the weighting calculation argument on it. I would rather say, so my point of view would be rather to say, we are living in, it's more likely that we are living in very extraordinary times today. And which means that these times will not continue like this. We see signs for that in several places. And under this assumption, maybe we have a rather limited window of time in which we can do certain things like interstellar travel. So I rather see it under this perspective, that we are facing rather headwinds ahead of us rather than winds carrying us further.
Yeah. So then, did we miss anything? I mean, wormhole.
What
I
the
mean,
weight
again, like I'm
calculation?
not talking about the exotic type stuff, which is the realm of science fiction, and there's no feasible prototypes. We're sort of sticking to, unless you want to, like if there's a lot of, if you want to talk about Alcubierre drives and so on, but I'm trying to stick to sort of the practical engineering ideas that are
Yeah,
out there so far. Does that have we covered them all? Do you think?
I was just thinking, if we really think about propulsion, which gets us to the relevant speeds, which I would say maybe 5%, 10% speed of light, then I guess we have covered.
Okay. So then I guess I want to shift gears first and just talk a bit about Project Lira as a cool idea to sort of test out some of these ideas. So what is Project Lira?
Yeah. So the main objective of Project Lira is to assess the feasibility of missions to interstellar objects such as Oumuamua. But we also looked into a potential mission to Borisov and other potential future interstellar objects. We initiated that project in 2017, shortly after the discovery of Oumuamua. And we published, or we released the first paper assessing the feasibility of a mission to Oumuamua just 2 weeks after, or 3 weeks after the discovery of the object, demonstrating that it would be possible to fly to Oumuamua with existing or near-term technologies.
So sort of describe what a mission might look like to do this, to reach Oumuamua.
Yeah, so most mission concepts are based on what we call the solar Oberth maneuver. So we would launch the spacecraft, and the spacecraft would then actually almost like fall into the sun. Yeah, so it would go to a trajectory and get very close to the sun, and then at the closest point to the sun, we are igniting the propulsion system. So in our case, it would be like solid propellant propulsion system because it's very reliable. And then the spacecraft gets like catapulted out of the solar system at extremely high speeds. Now, the reason why this is a very efficient maneuver is because if you ignite your propulsion system at this closest point to the sun, you get the maximum bang for the buck, according to orbital mechanics. And that maneuver would actually allow us to fly at about 70 kilometers per second or even faster in interstellar space. Just to put that in context, Oumuamua is traveling at 26 kilometers per second in interstellar space. So if we wait long enough, that spacecraft could essentially chase and reach Oumuamua.
And would you be looking to do a flyby of Oumuamua or an actual rendezvous?
Mm-hmm. So we looked primarily into a flyby for the simple reason that in order to get to Oumuamua, you have to be very fast. But if you want to rendezvous with Oumuamua, you have to be at the same speed as Oumuamua, which means that you would need to decelerate. Now, decelerating in interstellar space is quite tricky. You could do it, for instance, with a magnetic sail, so decelerating against the interstellar environment. However, because mag sails have a relatively low maturity today, we said that, okay, it's much easier to do a flyby and just stick to it because then we could do it with existing or near-term technologies.
Right. And so I'm sort of envisioning, like I'm thinking about, say, the Parker Solar Probe and how fast it had to fly to be able to get close to the sun. The sun is the hardest place to get to in the entire solar system. So I'm assuming you've got to have a really powerful rocket to even get you on that trajectory that takes you close to the sun, or maybe a bunch of flybys first of Venus and Mercury and Earth and so on. And then you have that solid rocket booster fire to kick it in. So is there a way to do it without that flyby of the sun?
Yeah, that's a good point, because we just published a paper on the possibility of launching a mission to Oumuamua without the solar Oberth maneuver. And actually, there are several options. There's a maneuver which Adam Hibbert, who is in our team, named the double Jupiter flyby maneuver. And
Wow.
with that maneuver, it's actually possible to get to these speeds without the solar Oberth maneuver. But there are several other flyby maneuvers where we wouldn't do an Oberth maneuver and still would be able to reach.
Yeah. There was an interview I did about 6 months ago, maybe. Someone was proposing that you take an RTG reactor and you just bolt it onto an ion drive. And so the spacecraft is literally just RTG and ion engine. And they figured they could get delta V's somewhere in the 200 kilometer per second range, enough to reach Oumuamua, do science, and even return samples back to Earth. So it feels like with some, and that's a fairly simple machine, you know, I mean, those RTGs are very dependable. Because Oumuamua is so weird. Like the first interstellar object that we have detected is unlike anything we have in the solar system, and is unlike the other interstellar object that was totally normal. So a lot of people say, like, oh, instead of trying to chase down this rock that's flying away from us, doesn't it make more sense to wait for something else? But do you think Oumuamua is something special, something that's really worth investigating specifically?
Yeah, good question. I mean, the simple answer is we don't know, because
Maybe, yeah.
Yeah, because we've seen Borisov, which the second interstellar object, which is much more similar to bodies we are observing in our solar system, and Oumuamua really seems to be a kind of oddball. And I would say, because we don't know and we've never seen that type of object before, we could end up with many such objects traveling around in interstellar space, but it might also be possible that the exact opposite is the case, and these objects are very rare. Now, the question is, do we want to take that chance? Yeah, maybe we will observe a similar object like in, I don't know, 10 years, 100 years,
Right.
or it's maybe something very special. So, so for me, it's a kind of question of how much is it worth it, and do we want to take the chance to potentially miss a very unique object?
Right. But I mean, people talk about being patient. It's a long mission to get there.
Mm. Yeah, we are talking about mission durations of maybe 16 years or longer. Actually, the longer we would wait, of course, the longer it would take to reach Oumuamua. But I would say mission durations between 16 years, 20 years plus. That's like the duration we are talking about.
Yeah. All right. So A.V. Scott and Flower is asking in the chat, and this maybe is one of the propulsion systems that we forgot to talk about. What do you think about the potential of metallic hydrogen as a fuel source?
Yeah. Okay, so metallic hydrogen is a material which, or a state of matter, let's say. It's a state of hydrogen which occurs under extreme pressures. For instance, in the core of Jupiter, I think it's hypothesized that the core of Jupiter contains metallic hydrogen. People have actually looked into metallic hydrogen for propulsion in the past. And I think the ISPs, so the efficiencies I've heard about, if I recall correctly, they are on the order of like thousands of seconds.
Right.
Just to put that into context, if you use normal hydrogen, oxygen for your propulsion system, you have an ISP of maybe 460. So here we are talking maybe about an increase of like an order of magnitude compared to the best chemical propulsion system we have today. However, if we compare that to electric propulsion systems, I mean, they have like lower thrust, but we would easily be able to get into that thrust range. So I would say metallic hydrogen, I think there was some news a few years ago, I think from Harvard, that they generated metallic hydrogen in the lab. I think we're still far away from using metallic hydrogen as a propellant and also to store it in a stable way, because I think stability is a big issue with metallic hydrogen. And even if we could do it, then the efficiency of the propulsion system we would get out of it would be in a range which might already be covered by existing propulsion systems.
Right. So it would probably be a great replacement for a chemical rocket, but it wouldn't necessarily get us the kinds of velocities that we need to go to relativistic speeds. It would let us live in the expanse universe, but not necessarily Star Trek or some version of that. Yeah. It's just like, it's like you pretty much got to be going, you got to have a propulsion system that goes close to the speed of light to get any significant knocking off the time on those journeys. How has been the response from the space agencies to this idea of sending a mission after an interstellar object?
Yeah. So the space agencies have been actually very fast in terms of contemplating missions to interstellar objects in general. If you think about the Comet Interceptor mission by the European Space Agency, which is not a pure interstellar object mission, but rather focusing on long-period comets. But they have incorporated that interstellar object aspect quite quickly into that concept, into this mission concept. And to my knowledge, that mission is gonna fly. So
it's gonna go with Ariel. I think it's gonna fly with the Ariel spacecraft in 2028.
Yeah. So it's actually only on its way to my knowledge, and so that's already, I would say, a big step. Then the space agencies, in terms of Project Lira, the space agencies typically operate on a 10-year scale, which means that they typically ask for input from the scientific community at a certain point of time. For instance, last year we had or 2 years ago in 2020, we had the decadal survey from the National Academy of Sciences in the US, and everybody could essentially send a white paper to that survey. Then they would essentially analyze and evaluate these white papers, and that informs the future next 10-year strategy or roadmap of how to do, for instance, planetary or space exploration. Now, this process is like very formalized. And there are good reasons for that, because it's like public money which goes into it. So they want to make sure that it's as objective as possible. But the downside of the process is, of course, that it's very long. And if you make new discoveries, it tends to be rather difficult to bring in very fresh, very new ideas and concepts into that roadmap. Nevertheless, space agencies like the European Space Agency, they still have a kind of mechanism where they can infuse like new discoveries or react to new discoveries by missions which are conducted very quickly and which are essentially all the time open. They are not in this kind of 10-year roadmap. But what we are trying from the project Lira side is to get traction in the scientific community, because it's ultimately about the scientific community supporting such a mission. And once you get enough support from the community itself, then the space agencies will react.
And, whenever I talk to any astronomer, any planetary scientist, and talk about like what would it be like if you could do a sample return mission from Oumuamua or Borisov, like obviously that would be one of their greatest dreams, because now you're getting a sample of another star system that the scientific discoveries that we could make would just tell us like just so much about how the solar system is different from other star systems. But they sort of like, oh, but it's impossible. And I think the drum you guys have been beating is that it's not impossible. It's entirely feasible. The clock is ticking. It's getting farther and farther away, and so you got to start. But it's entirely possible with current rockets, current capabilities. There's no new magic that would be required, just the willingness to stick a tiny little spacecraft on top of a massive rocket and launch it. Right.
Yeah. So about the sample return, we looked into sample return in a very recent paper, which was published in Advances in Space Research, and it turns out that if you can do sample return if the interstellar object is actually in our solar system and you're launching at the right moment, then you can essentially like pass by that interstellar object and maybe grab some dust which was ejected from that object,
like stardust or something.
Yeah. So that's entirely possible. However, when it comes to sample return in terms of getting to the surface, landing on it, grabbing something from the surface, and then going away, then it turns out that very quickly you would need propulsion systems such as nuclear thermal propulsion. And that's also true for a mission to Oumuamua. If you want to do sample return, then you would need a nuclear thermal propulsion system for that.
Well, I'll send you a link after we do this interview to this the paper on the RTG connected to an ion engine, because I think it's two fairly simple technologies that work great together. So that might do the trick. So then what about the larger idea of an interstellar mission? I've got to assume, I mean, I know NASA is considering an interstellar mission, but interstellar in terms of getting out into the heliosphere, right? So that's possibly in the works, right?
Yeah, so from what I know, this mission proposal, the Interstellar Probe mission, is around for a fairly long time. Like in different, I mean, they're regularly updating the design, but the idea is there, like I would say, maybe like 20 years or something like that. So for a fairly long time now. So I'm not sure to which extent NASA is going to fund that mission or which stage it is. To my knowledge, I might be completely wrong here. To my knowledge, there's no dedicated funding for developing that mission.
No, not yet. I think it's coming out of Johns Hopkins Advanced Propulsion Lab right now, or Advanced Physics Lab. And it's, they're building the proposal, and same thing as part of the decadal surveys, they're delivering it. And I think the goal is to try to get out to, say, 1,000 astronomical units and try to sample the interstellar medium and get a sense of what it's like in between the stars. But it sounds like that would work well as a combination of something that would do an Oumuamua flyby, like first fly by Oumuamua and then go out to the interstellar space and then taste the interstellar space.
Exactly. I think one of the points where I think the Interstellar Probe mission seems to be get difficulties to get traction is that the science objectives, they might not be that disruptive as for other types of so-called flagship missions, so missions which typically cost a couple of billions. Typically, if you want to invest a couple of billions, you're expecting some really disruptive science happening during that mission. And for the Interstellar Probe mission, I think there are objectives such as exploring like the the boundary between the heliosphere and interstellar space, getting more data from interstellar space. But I'm not sure if the science objectives are like disruptive enough to justify the cost.
And so then what about the interest in some kind of actual interstellar mission? Is anybody out there accepting proposals for an interstellar, like to actually reach another star? Like what your team is focused on, is anyone ready to consider those proposals yet?
Okay, maybe I forgot one thing
Oh,
for
sure.
the question before, because you were actually asking about reaching Oumuamua. So my point is actually that if a mission to an interstellar object would be added to the Interstellar Probe mission, then maybe there would be that disruptive science.
Yeah, that's what I thought. Is that you could sort of put the two together. So maybe that's
Yeah.
the trick is have a hybrid flyby and an interstellar mission. Then that might do the trick. But yeah, so is a true, and this is why I don't like the name of calling it an interstellar probe, because it's just going out into the interstellar medium, not trying to get to another star. But is there any interest coming from NASA or ESA or JAXA or the Chinese space, anybody, on a true mission that would go to another star system, or is it just too science fiction-y so far?
Yeah, I think the idea is popping up from time to time. I think NASA, I think for a period of time, if I understood correctly, there was a senator who pushed an interstellar mission for the 100-year anniversary of NASA or some predecessor of NASA. So from time to time, there are like news that NASA would now work on an interstellar mission. I'm always a little bit skeptical because oftentimes when the question comes how much budget has been allocated to these missions, then it turns out that either the budget did not pass, I don't know, Congress, or it's not in the budget,
right?
Or if there's a budget, it's really just for feasibility studies or developing maybe a component technology. So I would say right now it's rather the private entities like Breakthrough Starshot, Breakthrough Initiatives who are pushing interstellar research. I'm not aware of any initiatives coming from the space agencies, like really substantial efforts to push true interstellar missions.
So if people are, I mean, I think a lot of people are excited about this idea. Obviously, we've been watching too much Star Wars and Star Trek, or maybe not enough, I'm not sure. And we love the idea of humanity reaching other star systems, first with our robots and later, ideally, with our human astronauts. So if people want to participate and support the work that you're doing at the Interstellar Institute, what's the best way for people to get involved?
Yeah, so the first step to getting involved is just getting in touch with us. You could, for instance, just write me an email and then introduce yourself, your background, etc. And we really have a lot of areas where we would need help. Of course, we have all the technical work going on, but we also have an educational committee, for instance, where we do outreach. We give lectures at universities, but also at schools. We also have people working on Principium, which is our magazine, the dedicated interstellar magazine, where we are looking for authors, providing input to that magazine. By the way, this magazine is also for free, so you can download it. It's like, I don't know, between 60 and 100 pages.
Yeah, it's amazing. Yeah, I enjoy it every time.
Yeah. So there are many different areas where we would welcome any support.
So place your bets. What year do we see the first picture of an extrasolar planet captured by a spacecraft that we sent?
Yeah, so let's again take Breakthrough Starshot, just because this is like the most I would say the most serious attempt to get us to true interstellar travel. I think right now they are planning with a first launch date around maybe 2040, something like that. Yeah, so changes, but let's assume it's like 2040. Then if we assume a flight duration of between 20, 30 years to the Alpha Centauri system, then we are talking about getting the first picture back in like 2000, between 2060 and 70.
Perfect. I'll be like 90 to 100 years old. So it'll happen in my lifetime.
I mean, of course, it takes like 4 years to get the picture back.
Right,
so
of course, yeah.
Add that on top of that, but it doesn't make that much of a difference. So I would say this is like definitely the second half of the 21st century. And I would say, yeah, it's like 2060, 2070, if we are optimistic.
That's amazing. Yeah, it's a great goal. I absolutely wish you guys luck, and let me know when you're ready to launch. If people want to find out more about what you're working on, what's the best place to track your work?
Mm-hmm. Yeah, so we have a website, i4s.org, which is the go-to place for anything related to the Initiative for Interstellar Studies. If you want to get regular updates, then we also have a Facebook page, we have a Twitter channel. So these are the places where we release very recent news, but you should also find like the most recent stuff in the news section of our website.
Fantastic. Well, Andreas, thank you so much for taking the time to chat with me today. It's exciting. I definitely would love to see a mission. I would love to see those first pictures in my lifetime. So no pressure, but it's all on you to figure this out.
You're going to make an effort.
All right. Thank you so much, and take care.
Thank you very
Good
much
luck.
for having me.
Bye-bye.
Bye.